So if you break your arm, an X-ray gives you this really clear, undeniable picture of the fracture, right? You point to that jagged white line, you sink the bone, and you fix it.
Right, it's totally objective.
Yeah, exactly. But right now, the artificial intelligence systems that we're starting to trust to, write our code, assist our doctors, draft legal documents, they're basically operating without an X-ray machine. When they hallucinate or make a mistake, they just fail completely in the dark.
Yeah, they do. And it creates this landscape of, I guess, diagnostic muddy waters, because we are deploying these incredibly powerful models into environments where precision is non-negotiable. Yet the tools we use to double-check their work, they offer almost zero visibility into how they actually reach their conclusions.
Scary. Well, welcome to today's deep dive. If you're joining us, your mission is probably the same as ours, staying well-informed without drowning in information overload. And today, we are looking at a major bottleneck in deploying AI out into the real world.
Really big one, yeah.
Specifically, we're talking about hallucinations and the systems designed to catch them. We are diving into a fascinating new state-of-the-art paper. This is from the ICML 2026 workshop on trustworthy AI for good. And the paper introduces an architecture called SEVA.
Right, SEVA, which stands for Self-Evolving Verification Agent with Process Reward for Fact Attribution.
I know it is a very dense title.
It's a mouthful, for sure, but the implications are just, they're transformative for anyone working with generative models.
And here's why you should care. Like, if you are prepping for a meeting on AI deployment, or if you're just insanely curious about AI safety, understanding this shift is essential. We are actively trusting AI in high-stakes domains, finance, law, healthcare.
Absolutely.
But right now, the systems designed to fact-check these AIs, they are complete black boxes. So today, we are breaking open that box to see what accountability actually looks like.
Yeah, and to really appreciate what SEVA accomplishes, we have to look closely at the status quo of AI fact-checking first.
Okay, let's unpack this. What are we currently doing?
So currently, the industry relies on systems known as fact attribution verifiers. Think of like MiniCheck or ClearCheck. They're basically models acting as safety nets. But they share this fundamental limitation, which is they only output a binary label.
By binary, we're talking about just a simple yes or no response to whatever claim the AI just made.
That is the extent of it, yeah. You feed the verifier a claim and a source document, and it essentially just spits out true or false. Or, in their terminology, attributable or not attributable.
Okay, wow. So no explanation at all.
None. So if the verifier flags a claim as false, the generative AI has literally no basis for self-correction because it doesn't know why it's wrong. And even worse, a human operator can't audit the decision because the reasoning process is entirely invisible.
This sounds like a math teacher who just puts a giant red X on your test.
Mm-hmm.
Like, you failed, but you have no idea if you messed up a fraction, forgot a negative sign, or just wrote down the entirely wrong formula to begin with.
That analogy captures the frustration perfectly. I mean, in safety-critical deployments, an uninterpretable verifier undermines the very trust it's supposed to provide.
Because you can't verify the verifier.
Exactly. If a system just says no to a medical claim, a doctor can't do anything productive with that information, so SEVA abandons that binary label approach entirely.
Right.
Instead, it introduces this structured four-part output that's designed from the ground up to make verification auditable and, honestly, most importantly, diagnosable.
Okay, so if the giant red X doesn't work, what is this new system actually handing back to the user to make the decision auditable? Let's go through the four parts.
Sure. So it starts with evidence alignment, and this forces the agent to anchor its judgments in specific text from the source document rather than just, forming a vague, holistic impression of the text.
Got it. So pointing to the exact sentence.
Exactly. Then secondly, you get a reasoning chain. So the model has to trace its logic step by step.
Showing its work, basically.
Yep. Third, it outputs the final label alongside a calibrated confidence score.
Okay, and the fourth part. Because I feel like this is what actually gives the AI or the human user a path forward when things go wrong.
Right. The fourth part is the error diagnosis. If a claim fails and gets that not attributable label, SEVA doesn't just stop at the red X. It identifies the failure using a taxonomy of 6 exact errors.
6 errors. Like what?
Things like numerical exaggeration, negation flip, scope inflation, temporal shift, entity substitution, or just outright fabrication.
Wow, that's specific.
It is. And after identifying the specific category, it actually suggests an actionable fix to correct the claim.
Okay, we should ground this with a specific example from the source material, because the granularity here is really impressive. Imagine an AI generates the claim. 60% of participants significantly improved, but the actual source document provided to the AI simply says 60% of subjects showed improvement.
Oh, yeah, that is a very common, subtle hallucination. The AI just sort of spices up the text.
Right. And it's one that a standard binary verifier misses the nuance of completely. It looks at that claim and just outputs, no, not attributable.
Which is useless.
Exactly. But SEVA looks at it and outputs an evidence alignment, showing that 60% of participants matches the source text, 60% of subjects.
Yeah.
Then, in its reasoning chain, it notes that the word significantly has no source evidence whatsoever.
Right.
Finally, it diagnoses the exact error as scope inflation, and it tells the user to remove the word significantly.
It's the difference between a smoke alarm just blaring at you indiscriminately and a system telling you exactly which wire is smoldering behind the kitchen wall, and giving you instructions on how to safely disconnect it.
Yeah, that's a great way to put it.
It literally provides the receipts for every single decision.
Which raises an obvious question for anyone listening. If this structured four-part output is so incredibly useful and transparent, why haven't developers been doing this all along? Like, why is this just happening now?
Well, training a model to output this kind of complex multi-step structure is a massive technical hurdle. It's really hard.
Oh, really?
Yeah. When researchers try to train an agent using reinforcement learning, specifically this method called GRPO, with a traditional binary reward, the training just completely stalls out. The model fails to learn anything.
I'm stuck here. Wait, if the AI gets the logic beautifully laid out in its reasoning chain, but fumbles the final label and gets a 0, wouldn't it just keep trying until it eventually stumbles on the correct label? Why does a 0 completely break the learning process?
To understand that, we have to look at how these models actually learn from their mistakes. In reinforcement learning, the system relies on variance.
Variance.
Yeah, the mathematical spread of the scores. It uses that to figure out which direction to adjust its internal parameters. That directional signal is called the gradient.
Okay, gradient, right.
So under a binary reward system, the AI might generate, say, 8 different responses. If it misses the final label on all of them, or even if the formatting of its complex code is just slightly broken, it gets a 0 for every single attempt.
Oh, so if everything scores a 0, there is no variance.
Exactly. No variance means no gradient. The directional signal dies entirely. The AI basically has no breadcrumbs to follow to realize that one of those attempts had a brilliant reasoning chain and was actually very close to being perfect.
Wow.
Yeah, this phenomenon is called advantage collapse. After hundreds of training steps, a model trained this way remains completely stagnant because it just can't distinguish between a highly logical response with a tiny formatting error and unparsable total garbage.
It's like trying to navigate a complex maze in pitch darkness where the only feedback you get is falling off a cliff at the very end. You have absolutely no idea which of the 100 turns you took was the wrong one.
Which is why the researchers had to invent what they call a process reward. Instead of grading the final answer, they basically decomposed the verification quality into independent components.
So they graded the steps.
Right. By heavily weighting the reward toward the process, the formatting, the reasoning chain, the alignments, they essentially paid the AI to show its work rather than just grading the final outcome. Specifically, they used a 70-30 split.
Okay, so how does that 70-30 split actually change the AI's behavior during training?
Well, on the 70% process side, the AI gets 10% of its score just for formatting its output correctly, just ensuring the system can actually parse the text.
Like getting points for spelling your name right on the SAT.
Sort of, yeah. And it gets 30% for proper evidence alignment, anchoring its thoughts to the source. And it gets another 30% for building a coherent reasoning chain.
Okay, so that's 70% just for the process.
Right. Then, on the 30% outcome side, it only gets 15% for guessing the correct final label and 15% for an accurate error diagnosis.
And there's also an asymmetric calibration term baked into that score, right?
There is, yeah. It rewards the model for being highly confident when it is correct, but it heavily penalizes the model for being overconfident when it makes an error, which is absolutely crucial for real-world applications.
Oh, for sure. Imagine a medical AI that is 99% confident about a totally wrong diagnosis, or a legal AI hallucinating case law with absolute certainty. That's a disaster.
Right. It needs to know what it doesn't know.
The system needs to know when it is unsure. So under this new process reward system, let's look at our maze again. If the AI writes a beautifully formatted response, aligns the evidence perfectly, builds a flawless reasoning chain, but just fumbles the final label, It doesn't get a 0 anymore.
No, it gets partial credit for the genuine verification work it accomplished. Instead of a 0, it gets about half credit, a score of roughly 0.63 out of a maximum 1.2.
It restores the gradient. The AI now has a smooth, climbable hill of improvement instead of a sheer cliff. And the results are impressive. By switching to this process reward, they got the AI to produce perfectly parsable output 100% of the time, up from just 72%.
What's fascinating here is the implicit curriculum that emerged once this scoring system was turned on.
Implicit curriculum.
Yeah, the researchers didn't explicitly program a schedule telling the AI what to learn first, but by forcing that 70-30 split, the AI naturally learned how to verify before it learned what to predict.
It's like learning to drive a manual car. First, you just spend weeks figuring out the clutch and the gear shift without stalling in an empty parking lot. That's the behavior. Only after the clutch becomes second nature do you actually care about navigating through traffic to get to the grocery store, which is the outcome.
That's exactly what happened, and the hard numbers from the training process prove this out beautifully. Early in the training, around step 150, the model almost entirely mastered the format and the alignment.
Wow, that fast.
Yeah, its formatting compliance hit 100%, practically flawless valid JSON. It learned to work the clutch perfectly. But its actual overall accuracy, its ability to get to the grocery store, the F1 score kept steadily climbing all the way to step 350, long after those formatting skills plateaued.
So it learned the structure of a good argument before it learned how to consistently win the argument.
Exactly.
And the scale of this success is notable. The researchers used a relatively small 3 billion parameter model for this SEVA 3B, and it matched the performance of OpenAI's massive GPT-4 Mini on the ClearFacts benchmark.
Which is huge.
Yeah, a 69.0 versus 69.8 F1 score. But it did so while dropping format errors from 28% to less than 1%, and producing those entirely transparent, auditable receipts we talked about.
Which perfectly sets the stage for the self-evolution loop.
Oh, this is my favorite part.
Because if SEVA can perfectly diagnose its own errors with granular detail, we have to ask what happens if we feed those diagnosed errors back into the machine so it can teach itself.
Right. It goes through a loop that looks a lot like a student cramming for a test. First, it takes a practice test, that's the verify stage. It analyzes a set of claims to see how it performs. Then, it grades itself to find its weaknesses. That's the reflect stage.
Right, using those exact 6 error categories.
Yeah, it builds a weakness profile based on those categories, like scope inflation or numerical exaggeration.
So let's say it reflects and finds a glaring weakness in entity substitution.
Like constantly confusing Marie Curie with Alexander Fleming when fact-checking the discovery of penicillin in 1928.
Exactly. Then, in the probe stage, it actively generates adversarial examples targeting that exact weakness to drill itself.
It essentially writes its own custom homework.
Yes. If it knows it struggles with entity substitution, it allocates its training budget to generate 3 times as many tricky adversarial examples involving swapped names compared to a category it's already mastered.
That is so smart.
And finally, in the refine stage, it retrains itself on this custom-generated hard data.
Here's where it gets really interesting. You run this loop, you let the AI continuously analyze its own weaknesses and generate custom homework to drill its blind spots. You would expect it to eventually become a flawless general-purpose fact-checker.
Right, that's the logical assumption.
Like an ultimate decathlon athlete who just leveled up all their weak events. But it doesn't. After 4 rounds of this on a larger 7B model, it didn't become a generalist at all. It became a hyper-specialist.
It is arguably the most unexpected finding in the entire paper. The researchers basically assumed monotonic improvement, the idea that as the model self-corrected, it would just get strictly better across all categories.
Just a straight lineup.
Right. Instead, they found a sharp asymmetric trade-off.
But wait, the final round of rigorous training, the Mega FT round, used 4 times the amount of training data as the earlier rounds. We are talking about nearly 7,800 adversarial samples. Doesn't throwing a massive amount of targeted data at the model eventually smooth out those wrinkles and make it a generalist?
It definitively does not. The trade-off is deeply structural. It's induced by the distribution of the data it generated for itself. It is not a simple case of overfitting to a small data set.
So it's baked into the process.
Yeah. To put it in perspective, performance on the Hallucinations benchmark, which tests general hallucinations, shot up by almost 15 points. But at the exact same time, performance on truthful QA, a benchmark testing subtle nuances, plummeted by over 12 points.
Oh, wow.
Yeah. Multiplying the training data by 4 didn't close this gap. The model just doubled down on its specialized behavior.
We need to make this concrete because understanding this trade-off is crucial. The paper highlights a specific example, the case F3 example, involving a claim about carrots. The generated claim is, eating carrots significantly improves night vision.
Ah, yes. The classic carrot myth, complete with a subtle qualifier.
Now, the Truthful QA benchmark it failed on is designed to heavily test those qualifiers, words like significantly. Initially, before the AI went through its self-evolution loop, it correctly caught this claim as unsupported.
Because it noticed in the source text that while carrots help maintain normal vision, they do not significantly improve it above normal.
Right. It caught the tricky qualifier perfectly. But then it went through the self-evolution loop and built its custom homework.
And in that loop, it realized its major weakness was catching fake numbers and swapped names.
Yep. So during the probe stage, it bombarded itself with entity and numerical perturbations. It spent all its energy training its neural pathways to catch Alexander Fleming versus Marie Curie.
And as a result, it essentially got lazy on qualifiers.
Exactly. After the self-evolution training, it looked at the exact same carrot claim and falsely flagged it as completely true. It was so laser-focused on checking the core entities, making sure carrots and night vision were in the text, that it completely ignored the word significantly.
If we connect this to the bigger picture of machine learning, this is a profound realization about decision boundaries. When you force a model to hyper-focus its learning on specific structural weaknesses, it inevitably shifts the boundaries of how it evaluates text.
It literally overwrites its past skills.
Yes. By learning to be incredibly sensitive to one type of hallucination, like a swapped name, it unlearned its sensitivity to another, like an exaggerated qualifier. It became a specialist tailored entirely to the exact failure profile it generated during its reflection phase.
So what does this all mean? For you, the listener, let's bring this all together. First, we've learned that you cannot train a complex AI agent with simple binary rewards. A red X doesn't teach a student how to do algebra, and a zero reward doesn't teach an AI logic.
The reward granularity absolutely must match the output granularity.
Right. If you want a complex, auditable output, you need a multi-part process reward that pays the AI to show its work and prevents that advantage collapse we talked about.
And second, this structured output is not just a training trick to make the AI better. It is a dual-use asset. It creates the foundational substrate that any trustworthy deployment requires.
It gives us the X-ray machine.
Exactly. It gives human operators the auditable trail they need to actually trust these systems in high-stakes environments, whether that's a hospital floor or a legal review.
And the takeaway here is incredibly practical. The next time you are in a meeting and someone claims a new generative AI tool has been fact-checked or has a robust verification layer, you need to ask how. You should demand to see the receipts.
Never just accept a black box green checkmark.
Right. Demand the evidence alignments, demand the reasoning chains, and demand the specific error diagnosis. If the system cannot provide that level of granularity, it is not truly verifiable, and it certainly isn't ready for a high-stakes deployment.
And, the self-evolution loop also raises an important question about the whole trajectory of AI development. This research exposes that when AIs self-improve by targeting specific weaknesses, they inevitably develop blind spots elsewhere.
They don't become gods, they become specialists.
Exactly. The self-evolution process didn't create a perfect, all-knowing generalist. It created a hyper-specialist constrained by its own self-generated curriculum.
Which leaves us with a pretty provocative thought to chew on. Building on this paper, if artificial intelligence inherently drifts toward becoming hyper-specialized when it self-evolves, maybe the ultimate goal of achieving one massive, omniscient artificial general intelligence, the mythical AGI, is fundamentally flawed.
It certainly challenges the prevailing industry assumption that we can just, scale our way up, throwing more data and compute at a single monolithic model until it understands everything perfectly.
Perhaps the future of human-level AI isn't one giant all-knowing brain. Maybe the future looks more like an internal courtroom, a system made up of highly specialized, narrow SEVA agents, one optimized entirely for catching qualifiers, one optimized for entity verification, one for temporal shifts, all endlessly arguing with each other over who gets to be right, passing their structured receipts back and forth until they reach a synthesized verdict.
A team of highly calibrated specialists checking each other's work, rather than a single generalist trying to do it all.
Just like a hospital, you wouldn't want a general practitioner doing your brain surgery. even if they have the X-ray in hand. You want the specialist who spends every single day looking at that specific type of fracture. And as we've learned today, making sure that X-ray machine actually shows us the murky details is the only way we'll ever know what we're really looking at in the dark.